Hello everybody, my name is Raheel Chaudry, that's Kevin Alvarez, and this is Guerra, and today we'll be talking to you about the IDG service provider.
So UTC Aerospace Systems in Miramar, Florida, currently services around 200 IDGs a month. These IDGs are being serviced by an actual test stand. The test stand is actually introducing a lot of air into the oil for startup, and aerated oil can actually cause damage. So basically, what is an IDG? An IDG is an integrated drive generator, and basically what it does is it takes mechanical energy from the engine and turns it into constant frequency AC power for the aircraft. Our project will be to design and build a prototype of a servicing cart that can be quick and efficient, can service over 200 IDGs, and also be ergonomically friendly to the operator and be mobile, so it can be used in different test stands.
So the motivation for this project is to improve current IDG servicing procedure, as well as reduce failures within IDGs and improve overall aircraft safety. Aeration occurs when there's air that seeps into the system, either through leaks in the seals and fittings or through the oil itself. Aeration can speed up fluid degradation, which can cause loss of lubrication, cavitation, overheating, the hammer effect, and burning up of the seals.
In our research, we found several different ways we can reduce or prevent aeration. The three methods that we're going to focus mainly on is reducing the size of the pump from the current test stand, which is very powerful and is adding a lot of turbulence to the oil, so reducing the pump should help mitigate that, as well as using an adequately sized reservoir. If a reservoir is too small, the suction from the pump is going to cause a lot of turbulence in a small tank, as well as making sure there's no dirt in the system, so we will include a filter which will remove any contaminants because aeration, air bubbles tend to form around the particles in the oil. And finally, our test is going to revolve around density and volume to measure the aeration content of a sample.
So we went out into the market to see what kind of carts we're actually competing with. This is a servicing cart from Tron Air. It costs about $6,000, and it actually has a manual pump. We also got another quote from Hydraulics International. They gave us a quote for an electrically driven pump that it was about $8,000. So our job was to come below these prices. So some of the standards that we had to implement was ATA Chapter 24. Chapter 24 of the ATA codes deals with everything that has to do with electric power in the aircraft. We also had to follow the quality standards of UTOS, which is an ISO 9001 and an AS 9110 site. They're also an OSHA Volunteer Protection Program plant, which focuses on employee safety, as well as any technical data that we use for the project had to be export controlled. So we have to follow those things. Like I said before, the biggest standard that we had to follow was the ATA Code Chapter 24. They are an FAA Part 145 repair station, so we have to follow all those federal regulations. Our gauges are all calibrated, and they're in the calibration program under UTC Miramar, so they are calibrated once a year. And all of the standards that we use for the oil that were found in the safety data sheets for it are listed here. When we actually built the prototype, we had to follow MPT threads and SAE threads for all of the things that we had to put together.
So the design specifications for this project are to deliver deaerated oil at less than 35 psi into the IDG, as well as deliver 4 to 5 quarts of oil at less than a minute into the IDG, comply with industry standards, be compatible with Eastman Turbo Oil 2380, which is used in the IDG, as well as be ergonomical, mobile, and cost effective. So if you look here to your left, we have our initial designs. The first one is, on the left, is similar to the Tron Air, where it's on a handcart with our reservoir at the bottom and custom filtration system, pumps, gauges on the top level. On the right, we have a 4-wheel cart design to be more ergonomic. The reservoir, custom filtration system, pumps, gauges is all incorporated into that. So for our final prototype design, we did choose the second preliminary design, but instead we made some modifications down the line to improve later on. So for our static analysis, we started with a 12-gauge steel cart. We applied the maximum load that the cart would see, meaning a full reservoir, tools, pumps, tubing, custom filtration system, everything that we would expect to be on the cart. And we saw that there was minimum deflection in the cart, as well as trying to lower the center of gravity to prevent tipping over of the cart.
Our flow analysis starts with the pump we selected. We selected the Aero Pro 1/4 inch air diaphragm pump. Now, our operating point is going to be supplying 30 psi of compressed air, which is readily available around the facility and considered safe to use. That's why we chose that. And our flow rate is going to be around 1.35 psi. And according to the manufacturer's pump curve here, it gives us a pump head of around 11 psi. So starting with that, we use Bernoulli's equation to find the theoretical output pressure of the oil into the IDG, and we identified all the parameters needed to analyze it, such as the velocity, which is 2.2 feet per second, based off of the 1.35 flow rate and the half-inch diameter of our pipe network, as well as the major and minor losses, including all the contractions, expansions, and elbows, and so forth. And finally, we did some additional testing to characterize how much pressure we lose from our filter. We tested the filter using a range of 1 to 1.5 gallons per minute, and we measured that we lose about 1.0 psi due to the filter. Overall, our theoretical output pressure into the IDG is just over 6 psi.
So for our prototype construction, we did start with a 3-tier cart. We removed the second tier in order to utilize this drill press to drill the mounting points for the reservoir, the pump, the custom filtration system, as well as the tubing that would go from the reservoir into the pump. We kept the second tier removed as is for further expansion to an overflow tank that would be added right next to our reservoir, as well as to make it easier on refilling the reservoir after completion. Oh, and being empty. Here's our pump with the lines coming in from the reservoir and leaving it. Right here we have the custom filtration system base, which utilizes the filter that's used in an IDG to streamline maintenance, as well as that it's easily accessible within any UTAS facility. And it will give us a similar system to the IDG in terms of oil. Right here we have our completed fluid line system with our pump and totalizer to measure how much fluid we're actually putting into to get the IDG. A pressure gauge, which isn't depicted here, to our custom filtration system, to a Teflon hose with a quick disconnect to allow for accessible reach to the IDG. Here's a completed cart with a quick disconnect on the Teflon hose, the pressure gauge. Right here we have the air inlet to our pump with a quick disconnect that will come from the wall to a needle valve to control the air going into the air regulator to make sure that we're putting in 30 psi into the pump to run at the optimal point that we have chosen. So for our cost analysis, originally we had budgeted to spend $2,500 on the cart as a whole. We did spend $2,570, just a little over. Right here we have a labor cost that we calculated. Since this was an internal project to UTC, this is a calculated cost to show what UTC would incur if they were to outsource manufacturing and machining costs to a third party.
So for our testing, the way we tested for aeration content in the oil was we compared the test stand and the service cart side by side. We filled up a bucket with the oil from both the test stand pump and our pump, and we measured a specified volume, and then with that we measured the mass of that sample in order to calculate the density, as you can see in the right-hand column here. The test stand gave us about an average of 0.94 kilograms per liter, where the service cart gave us a slightly higher density of 0.96. Now theoretically, a sample that has more air content, taking up that oil's volume, would give a lower density. So a higher density would mean there is less air in that sample. Also, what we did was we started a stopwatch and timed to see how long it took for the air bubbles to rise up to the surface and dissipate out of the oil. As you can see from the test stand, we get a rough view of how the air bubbles behave in the oil. It took anywhere from 5 to 13 minutes for the oil bubbles to come up to the surface. Just watching it visually, the bubbles were coming up very slowly, and there was a lot of them. Whereas the service cart was significantly less. It did not go longer than 2.5 minutes, so there's a big improvement there. Just looking at it, the bubbles come up and rise very rapidly, and there's much less of them. Here's some performance data of the cart. We have a totalizer and a pressure gauge, so here's some data just as reference to see how accurate our totalizer is, as well as the pressure gauge readings, which varied from 3 to 7 psi. The reason for that fluctuation is because the pressure gauge will read and fluctuate as the pump operates between strokes. And we're getting a maximum pressure of consistently around high 6, low 7, which our theoretical was 6, a little over 6, but that was calculated after the filter. And since our gauge is before the filter, we would disregard that 1.0 psi pressure loss, which gives us a theoretical pressure of around 7 psi. Here are some pictures of the oil samples right after the test. As you can see on the right, the test stand clearly is much dirtier. But if you take a closer look, you can see the surface of the test stand sample is a lot more disturbed. There's a lot of tightly packed air bubbles, and there's a lot more of them when you compare that to the service cart, where there's not only less bubbles, but they're more spread out and they're a little bigger, and you can see the surface is much smoother. Here's another picture of the oil samples from 2 separate trials. Again, you can see the same thing. The test stand has a clear picture of more bubbles tightly packed when compared to the service cart. Overall, the density and the time in these pictures show that we have reduced air when we compare it to the test stand. The way we integrated global design into our cart is our pressure gauge and our totalizer can both read SI units and metric units, as well as including a French and Chinese user's manual. The reason for those user's manuals is because UTC has facilities in France and China that also service these IDGs. And ultimately, our goal would be to implement our cart into their testing procedures. Now, since those facilities are overseas, we would need to comply with the IAB regulations, or the International Air Transport Association regulations. For example, in their China and East Asia region, they have a strict pollution policy, which brings me to environmental issues. Our pump, since it's compressed air, driven by compressed air, we are completely clean and reducing, we have no pollution, right, whatsoever. Since we're dealing with hydraulic oil, which is dirty, we need to properly maintain that and make sure there's no spills. So in our design, our reservoir is properly sealed, and we have quick disconnect fittings everywhere, so we should be preventing all spills. And in the event of a spill, which it can happen, UTC has some contingency plans in place that we will follow.
So the biggest takeaway that we got from this project was how to take an idea and actually make it into a working prototype. We had to overcome a lot of challenges that were put in front of us. Working a lot with an actual working company, so we couldn't stop production in order to build this prototype. We actually had to find ways to work around it. Basically, to be cost effective, we also had to take into account all the labor costs that it would have cost if we hadn't built it ourselves, if somebody else would have built it for us, and also to actually plan the project out, which is what we did throughout the year. And I believe that we also divided our responsibilities between us pretty evenly. Orange being major duties, and then blue being auxiliary or subsequent help for the actual team. In conclusion, the servicing cart actually was able to meet all the requirements that it was set for. We actually decreased the aeration of the oil. We were pumping at a safe pressure into the IDG. And now, to actually get it into production, we have to develop some things. So we have to not only come up with the plans that he had spoke about before, but we also have to develop a standard operating procedure for it. We also have to get a total preventative maintenance program for this, so we can determine when to change the filters, when to check for leaks, which would be every time that you would use it and stuff like that. But mainly is to get an action item. And the action item from our service engineering in Rockford, Illinois would actually approve us to use this in the actual unit. So initial testing has been so successful that our the technical supervisor for UTC in Miramar has actually ordered a second cart. So this is actually a working prototype that has seen some good results. Thank you guys very much. Yes.
How often can you use your cart without it breaking down?
Breaking down?
So like, let's say, I'm assuming you're gonna have multiple units coming in. Can you actually support like using it once, stopping it, going to the next one, continuing testing? Or do you have to like wait a period of time, or?
No, not at all. No. So it has quick disconnect fittings. So in Miramar, they have 5 test stands. and the quick disconnect fittings will actually go to the pump and out of the unit, so you can actually disconnect them, roll it to the next stand, connect it to the new IDG, and actually pump oil into it.
And you're not concerned about overheating your compressor or?
No.
No, it's basically by the time that the car actually gets there, the test engineer would be putting on another IDG. So that would be your cool down period for our system in terms of if we were concerned about overheating. But since we are running at a low peak pressure and a low flow rate, we aren't considering overheating since there hasn't been a temperature differential in there.
So you can use it as many times as you want.
Yeah,
It's a cycle. I think his question is how
Yeah,
many cycles.
Yeah, no, definitely. So we only test about anywhere from 10 to 20 units a day. So that would be the amount of use that it would get. And with 2 carts, you would see half of that use. And when you're actually pumping in, you're only using it for about a minute or so, because an IDG is no more bigger than about this big. Yeah. Yes.
How did you arrive at $5,000 of labor?
Okay, so the biggest labor driver was actually the custom filtration system. That had to be machined out of steel. So it took the machinist approximately 2 weeks of machining to do that filter. So if you take into account what they would charge any other customer, which would be in an aerospace company like UTC, it would be around $100 to $125 an hour, then you would see that's the price that we got to. So it is a ballpark. The actual assembly of the cart, which was done by us, actually didn't take too long compared to a filtration system like that. That's why we went with 1 filter instead of 2, just to reduce the time.
Did you keep track of the time, not your engineering time, but the time that you drilled some holes, bolted it together?
Yes.
Did you guys keep a time slip for all the time you guys put in?
Yes, I did, but when it compared to the actual filter, it was negligent, because the filter took way longer.
But $120 an hour is $2 a minute.
Yeah.
So every minute you work is very expensive.
Yeah.
How about if you made 6 of them?
No,
Could you figure out a price for, say, hey, I want 6 of those, tell me what the price is going to be? Could you figure out what 6 would be rather than 1?
No, we didn't, but I think that we would get better at our manufacturing procedure, so.
No, I'm just saying, could you, from the data that you collected,
Yeah.
give me a price on 6 of those units?
If it was for internal use or external use?
That's a yes or no question.
Yes, we could.
Okay.
Obviously, this is your prototype.
Yes.
So
Yeah.
Just
It
get
can
it
be
off.
changed. It can be changed, yeah.
I have a question for each and every one of you,
Okay.
and I'll start one at a time. In your data, and I'll start with you, in your data on your test stand, you've got densities running between 0.99 to 0.94. That's a lot of spread compared to what you saw in the test stand itself. Did you look at that and try to figure out why they're different?
Well, basically, when we're running these 2 first for comparing the test stand, so our service cart test stand, as soon as it's a push button where you push the button and it just shoots oil out. So it's hard to actually just stop it where you want. So there's going to be inconsistencies of, like, say we're measuring 60 ounces, we're going to miss 60 ounces by a little. And then on top of that, we were using buckets to make sure we don't spill over all over the place. So the buckets had marks on there, but they aren't in increments of 1 ounce or something closer to what we were measuring at. So it's hard to make sure that we're hitting each mark. And that 0.9 shows, basically you can call it user error in a sense. That spread is also aeration, but combined with a bit of user error.
Yeah, because the time really shouldn't have an influence on a density measurement. I mean, if I fill the bucket with half as much or twice as much, I would hope it's steady state enough that they would be about the same. So I still have a hard time on it, because I saw the 0.99 said, that's almost perfect. What did you do right there that you didn't do on the others? So that's a comment. Next person I'll ask is, you presented some pictures of oil out of the test stand and then oil out of your system. Were the pictures produced with material processed with identical parameters? In other words, was it clean, were they both clean oil? Let me go there first.
Yes, so the test stand was a little bit dirtier, to begin with, it was.
So wouldn't you think that would influence how ugly it looked to us?
Yes, absolutely, but you can still see a lot of the air, the bubbles from the test, and you can see that the service card samples were a lot cleaner, not cleaner, sorry, less air bubbles, there's less.
Okay. And then the last question I'll throw to you is, one of the functions I think that's really important that I didn't see that you presented was how accurately it produced or provided a fixed volume of solution or oil to the system. Did you do any measurements or any tests where you logged in how much you needed to put and the output was measured to ensure that the volume out equals what you measured or you requested to put out as volume?
So, if I understand the question correctly, so if we had measured what we measured with the buckets and then with the totalizer, that's what you're saying.
Yeah, my concern is that I have a test stand. It holds 4 quarts of oil. I go in and I put on my controls 4 quarts of oil. Did I get 4 quarts of oil in my test stand, or did I get 4.5, or did I get 3.5?
So the way that they measure the oil quantity inside these IDGs is an actual sight glass. So it actually has a range that it could be on. So I cannot tell you specifically if an IDG takes 1.25 quarts of oil, because the procedure for that IDG to be serviced is to fill it up, to run it, and then to look at the sight glass. So the ultimate factor of the servicing card is to do the initial servicing of the IDG, and not to say a specific amount of oil in that system.
So this system does not control the amount of oil it's putting in to...
It'll be controlled by the operator. So that's why we have that valve that can actually shut down the pump, and then it will stop pumping oil into the system.
Okay, thank you.
Do you guys have any like fail safes for the system? Because you're still running under pressure, right? And if something fails, it'd be good to have like an emergency stop. So did you guys ever consider that in your system at all?
Yeah, so that's why we have the quick disconnect. So,
Well, I'm not talking about a quick disconnect, right? If for some reason some line fails and you have a rupture, your quick disconnect isn't really going to do anything. I'm asking more if like you have an emergency stop, because like in my experience, designing test stands for IDGs, they tend to have some sort of emergency stop or some sort of like kill switch so that the operator or the technician doesn't get hurt, or the engineer servicing the machine doesn't get hurt while he's trying to test it. And so in this scenario, it doesn't sound like you have that.
In our prototype, we don't, not yet, but that is one of the future works that we are implementing in our second design, our second cart that they had ordered. But this was just a prototype to reduce costs and give an initial, hey, this is what's actually working for ETC.
What are they paying you for the second cart? Did you get all your money? Did you get the 5,000 plus the all the parts?
no, well, they're not paying me because I actually work there, so no.
Oh,
It's one of the side projects I have there,
So you're going to fix all the safety issues?
pretty much.
I have one last question. It's a bit more on the calculation side, technical portion of the flows, Reynolds numbers, the impact, like he mentioned, the difference between the clean oil versus a fresh batch of new oil versus the oil in the test stand. Did you guys account for any calculations or differences in your Reynolds numbers, the Reynolds calculations with a dirty oil with X amount of contaminant versus the new one, what your fluctuations would rather be? If you had those, what was seen if you ever did those calculations? What changes did you actually saw versus one to the other?
Yeah, so ideally we would have liked to compare clean oil with clean oil, but we were unable to do that. And in our calculations, it's all assumed off of clean oil. And going forward, that would be something with more additional testing. We would definitely include that.
It's always something to keep in mind, because as you said, and it's one of the things that we have to look at, when you have contaminants in that oil, it is more prone to carry on more air bubbles to it, surface friction and surface tension along the size. And also for the sake of reducing any future cavitation issues on that IDG once you pump it in with, you know, a lot of contamination, possibly smaller than what the filter can actually filter out. Okay.
Did you guys actually run tests with the IDG service manuals in hand? And did you run it from multiple IDGs, like from multiple manufacturers, or is it just like one specific manufacturer?
So, as I said before, we're not allowed to actually test it on the IDG, but we're doing a preliminary testing. So, until we have that action item from service engineering, we're not allowed to use it on the actual
Did
IDG.
you use the service manuals
Yeah, of course.
for multiple manufacturers?
No, we only have one manufacturer, us, UTC.
You stated that you met the ATA Chapter 24 standards.
Yes.
What did you have to do to this cart in order to meet that?
So in order to be able to correctly service the IDG, you need to follow the component maintenance manual as well as the standard practice manual, and that all falls under the
So what are the unique things that you had to do specifically on this?
So in the standard practice manual, it tells you that you have to pump in oil at below 35 psi, that you have to do it in a way that it will not cause damage to the actual unit, and it had some other requirements that I don't remember off the top of my head. But yes, we followed everything on the standard practice manual.
So thank you very much.